Hello, this is Jack Jackson. In this video, we're going to continue our looking at a formal investigation of congruence of triangles. So let's remind you of a few things from our last playlist. First of all, what is the definition of congruent triangles? Well, there are actually two different ways you can do this. One is by looking at transformations and fitting congruence of triangles in a larger idea of transformations where we say two figures are congruent if and only if there is an isometry, identity, reflection, rotation, translation, or guide reflection that maps one geometric figure onto the other. Now, we're not going to take that approach in my class. We'll get to that later in one of the later playlists on transformations. For now, we're going to take the definition that two triangles are congruent if and only if all their corresponding parts are congruent. Specifically, we say triangle ABC is congruent to triangle A prime, B prime, C prime if and only if angle A is congruent to angle A prime, angle B is congruent to B prime, angle C is congruent to angle C prime, and the sides line segment AB is congruent to line segment A prime, B prime, line segment BC is congruent to line segment B prime, C prime, and line segment CA is congruent to line segment C prime, A prime. And so here you see some examples of some congruent triangles there in Euclidean geometry. So the major investigation that we undertook last uh, week that you did informally, and that we're going to continue working on this week, is um, even though it requires that all six corresponding parts of two triangles be congruent for the two triangles to be congruent, if it is hypothesized or we have proved that we have fewer than all six corresponding parts congruent, is there enough information there to completely determine that the triangles are congruent? What if you know 5 or 4 or 3 or 2 or 1? Is there enough? Well, it turns out that the crux of the matter we hopefully found out in our investigations last week was three parts. In Euclidean geometry, knowing 1 or 2 is never enough. Knowing 4, 5, or 6 is always enough, at least for Euclidean geometry. So we notice that we have a general type of question that we often ask in mathematics. What is a minimal set of conditions that must be met in order to reach some desired conclusion? In this case, we're asking what is a minimal set of known number of corresponding congruent parts, measures of sides and angles being the same, that is sufficient to conclude that the two triangles, or possibly a triangle with itself, are congruent. So there's two perspectives that we looked at this. One is look at congruence conditions. If we're given two triangles, so we know the two triangles exist, and we know that we're given corresponding parts that are congruent, do the two triangles have to be congruent? Okay, and then the measurement conditions, if we're given some specified measures for a given condition, does there even have to be a triangle that exists with those measures? And if so, how many different size triangles, in other words, how many different congruence classes of triangles can have those measures? So those are going to be our two main questions. We investigated this some last week and we're going to do it again this week. So the correspondence conditions, let's identify them. There's 6 of them. There's this SAS condition, or side angle side congruence condition. We say that a pair of triangles, or a triangle with itself, have the SAS congruence condition if and only if the two triangles are in correspondence, so that two pairs of corresponding sides are congruent, and the pair of corresponding angles included by these sides are congruent. And then the question is that condition enough to make the triangles actually congruent or not? And the answer may depend on which geometry we're in. Side, 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 or SSS condition, we say that a pair of triangles or triangle itself have the SSS congruence condition if the two triangles exist and they are in correspondence so that all three pairs of corresponding sides are congruent. The ASA condition is the angle side angle condition. That's if two triangles are in correspondence so that two pairs of corresponding angles are congruent and the pair of corresponding sides included by these angles are congruent. Notice that that's different than the AAS condition. We say the pair of triangles or triangle itself have the AAS, or angle-angle side condition if the two triangles are in correspondence so the two pairs of corresponding angles are congruent and the pair of corresponding sides opposite one of the pair of corresponding congruent angles are also congruent. The SSA condition is different than the uh, SAS condition. It says that we have a pair of triangles or triangle itself have the SSA, or side-side angle congruence criterion condition if the two triangles are in a correspondence, so the two pairs of corresponding sides are congruent, and the pair of corresponding angles opposite one of the pair of corresponding congruent sides are congruent. And finally, we have the AAA condition. We say a pair of triangles or triangles in itself have the AAA congruence condition if the two triangles are in correspondence so that all three pairs of corresponding angles are congruent. So the question is, given one of these conditions, is that enough to determine that the triangles are congruent? And I'll just give you a little bit of the punchline here. It turns out in Euclidean geometry, some of them work and some of them don't work. Some of them are sufficient to make the triangles congruent and some aren't. And I also say that in some of them, it depends on which geometry you're in, whether they work or whether they don't work. So that's what we're going, hopefully we've already investigated this before. We're going to investigate it more. And now notice a couple things. The labels correspond to congruent parts go around the triangle in order. This might be clockwise or counterclockwise for the first triangle, and it can be clockwise or counterclockwise for the second triangle, regardless of the direction around the first. So you can go clockwise around one, then either clockwise or counterclockwise around the other. These 6 congruence conditions take in all the possibilities. For example, SAA is the same as AAS, and ASS would be the same as SSA, and you can probably figure out why we prefer SSA instead of ASS. But the order does matter. For example, SAS and SSA are 2 different conditions. Okay, so when you have SSA, that first S and that A are opposite of each other, whereas this A is between the 2 S's. Okay. To use these, you have to say the 2 triangles actually exist, and a set of 3 parts of one triangle have to be congruent to the corresponding parts of another triangle or triangle to itself, and they do not require the parts of the triangle be congruent to each other unless the correspondence from a triangle to itself. So we should have been able to adequately answer these questions for the 4 geometries based on last week. So what we're going to do is continue working on that this week. And so we see here that we also can think of this a different way, and that is thinking of them as measurement conditions. We have the same 6 conditions, but we're thinking of them as measurement conditions now. So for example, when we have the side angle side or SAS measurement condition, we're given a length 1, an angle measure, and then a length 2 to indicate the measures of 2 sides of a triangle, the measure of the included angle. For example, a 2 centimeter, 1.3 radian, 5.6 centimeter triangle, or a 5 centimeter, 40 degrees, 7 centimeter triangle. And the question is, first of all, does even such a triangle exist? And if it does exist, are they all the same? If so, that's 1 congruence class. If a triangle doesn't exist, that's 0 congruence classes. Maybe you can make it where there are 2 different triangles, 2 different sizes, but every triangle has to be one of those 2 sizes. Well, that's 2 congruence classes, and so forth. And so we're going to ask that question about all these different conditions. And they're very similar to the congruence conditions. So side, 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 SSS, that means we're given the 3 lengths, for example, 2 centimeter, 4 centimeter, 5 centimeter triangle. ASA, we're given 2 angle measurements and a side, where the sides between the 2 angles, like 2 radians, 5 centimeters, 0.3 radians, or 40 degrees, 8 centimeters, 20 degrees. AAS would be also 2 angles and a side, but a different order. For example, it might be 2 radians, 0.3 radians, 5 centimeters, or 40 degrees, 20 degrees, 7 centimeters. The order makes a difference. Okay, so for example, even though these are the same three numbers as up here, right, the order is different. SSA, like SAS, is 2 sides and an angle, but this time the angles ought to be opposite that first side. So 5.6 centimeters, 2 centimeters, 1.3 radians means the angle with size of 1.3 radians, or it might give something there in degrees. It has to be opposite that side of length 5.6 centimeters. Okay, and then of course the angle condition is we're given all 3 angles. So it makes a difference what we have in terms of order. So the first thing we want to know is if these conditions even allow a triangle at all, or if they present an impossible situation. If it's impossible to make such a triangle, then there's 0 congruence classes possible for that particular combination of measurements. If such a triangle is possible, then Are all the triangles with those specific measurements congruent to each other? If so, there's just one congruence class possible for those specific measurements. Perhaps given set of measurements, there might be 2 or 3 or more, or maybe even infinitely many. And so we could identify that. One thing we might say is in general, if you're just given all the different possible measurements, what are the different possible congruence classes? Maybe it's 0, maybe it's always 1, maybe it's 0, 1, 2, maybe it's 0 and 1, maybe it's 0 and infinity, whatever. We'll try to figure those out. So now what we're going to do in the next series of videos, we're going to take each of these conditions, look at it first in Euclidean geometry, and then follow it up with looking at it in hyperbolic, spherical, and taxicab geometry, and determine which of these conditions are going to work for a congruence condition and guarantee the triangles are congruent, and which ones are going to work, what number of possible congruence classes you can have for each type of condition.